Parity is a simple form of a redundancy, which means an extra bit appended onto the code word to make the number of ones odd or even. So parity can detect a single bit errors. What it means is as follows. You have two choices of a parity, even parity or odd parity. Even parity in the code word, number of ones is even. Odd parity, number of ones is odd. This works as follows. When you send an information, suppose you have a 8-bit information, you add one more bit, so total 9 bits you send. You add one more bit such that number of ones in all 9 bits is either even or odd. And on the receiving side, you already have an agreement with the receiving side which parity you use, even or odd. Then in the receiving side, as the receiver receives an information 9 bits, if even parity is assumed, then you count the number of ones. If the number of ones is not even, then you can tell there was an error. Here we assume single bit error. Of course, a multiple bit error occurs, we may not be able to detect that. But by the empirical observation, when you send a block of information, bits of information, then chances are over 90% only one single bit error occurs. The chance of a multiple bit error is very small compared to single bit error. So having just one more bit as a redundancy called a parity is a very powerful mechanism to detect error in transmissions. So for example, suppose you have a 3-bit information. Then how do you make it even parity or odd parity? So suppose even parity first. Then if your message is 000, then to make all bits number of ones even, you have to add 0 here. For 001, you have to add 1 so that you have number of ones even. So you have to add 1 here, you have to add 0 here, 1 here, and 0 here, and 0 here, and 1 here. Then the total number of bits in the code word has always even. If you use odd parity system, number of ones has to be odd. So in this case, if original information is 000, then you would add 1, so that you have a number of ones odd. 0, 0, you would add 1, you would add 0, you would add 1, you add 1, and you add 0. So this is how you add parity for the even parity system or odd parity system given 3-bit original data. Gray code, if you recall, we discussed this one in earlier slide, has some special property. What is that? Two adjacent numbers, you have only one single bit change. Between 0 and 1, you have a one single bit change. 1 and 2, 2 and 3, including 0 and 9, the very first one and last one wrapped around, still you have only one single bit change. This is called gray code. Gray code, because of this special property, we can use this property in a very powerful way. For example, this is called optical shaft encoder. How this works is that behind this shaft there is a light source, and the black one means blocking the light, white one means passing the light. So based on whether the light is blocked or passes, we encode the value. So for example, if light source is behind this area, of course the shaft rotates though. So light source is here, all the lights are blocked. So we have a 0, 0, 0 as a value for that. But the shaft rotates, and then this segment is behind the light source. Then we have B2 blocked, B1 blocked, and B0 light passes. So the encoded value for that is 001, and so on. So from 0 to 7, this binary encoding is done, this optical shaft. But if you use a gray code is 0 is 000, and the 1 is 001, the 2 is 011, and the 3 is 010, and so on. Then the gray code for the optical shaft is something like this. We find a very interesting property, that is, suppose if you use a simple binary coding, and then the optical shaft rotates, and the light source is in between two areas, somewhere here. Suppose the light source is somewhere here. Then the most significant bit 2 could be either 0 or 1. And the second bit could be either 0 and 1, depending on the position of the light source. And the least significant bit, B0, could be either 0 or 1. Here, this is 1, this is 0. So, depending on the position of the light source, each bit has either 0 or 1 condition. So, it could be read as all zeros, 0, all ones, and 7. So it could be any value between 0 and 7. But if you use a gray code, the light source is in the similar position in between value of 3 and 4. But here, due to the gray code, we have a very interesting property. The most significant bit could be either 1 or 0. The second bit, because all passes light, is for sure ones and ones. And the least significant bit is all zeros. So, even if the light source is in between two value areas, you could read either 0, 1, 1 or 1, 1, 0. So either 3 or 4, which is the value we wanted to have encoded. So comparing those two encoding systems, simple binary code and the gray code eliminates the possibility of error due to the physical alignment. So this is the power of a gray coding system. So here is the explanation of those two cases. If you use a simple binary code, you have all possible values coming out because of the physical alignment. But if you use a gray code, you still have either correct 3 or 4. The Unicode is an extension of ASCII. ASCII originally designed for 7-bit encoding, so you can have up to 128 different encodings, but ASCII could be extended to 8-bit 1 byte, which covers up to 256, but still, considering all the alphabets and letters in the whole world, 256 is not enough to cover all the languages, so we use a Unicode for character coding system. The Unicode is based on 2-byte, 16-bit. So with the 16 bits, you can encode more than 65,000 character codes. So Unicode is actually used in Java programming language.